what do solar and wind power have in common? They're both intermittent. That's just a fancy word for saying the sun isn't always shining and the wind isn't always blowing. But we still want to use energy sources. They're renewable and carbon neutral. So how can these energy sources compete with fossil fuels, which supply energy on demand with the flick of a switch? Energy storage is the answer. My name is Matthew Labbe. I'm a PhD student in the Department of Chemical and Materials Engineering at the University of Alberta, and I conduct research related to energy storage. Energy storage is worth studying because it will allow us to put aside excess energy provided by wind and solar during their peak production times for later use. But what's energy storage? Well, batteries are the best example. We store energy into a battery so we can use it later when we don't have access to an energy source. Take a flashlight, for example. You don't plug that in when you're camping. You rely on batteries to give you the power when you need it. It's the exact same in terms of energy storage for wind and solar. We can add large batteries to the power grid that fill up when the wind is blowing, so that when the wind stops blowing, we can still use that renewable energy. Okay, so we need large capacity batteries for grid-scale energy storage. A large stack of lithium-ion batteries would be good. Well, unfortunately, that's not the most feasible answer. What we need is innovation into another battery type, one with the ability to store more energy per kilogram of material, energy density as it's known. One possible contender lies with Zinc-Air batteries. These devices use solid zinc metal and oxygen from the air. The best part is don't even store the air, it's everywhere, so the battery's energy density is based only on the zinc, and it can provide some of the best energy density out there. Okay, so a few Zinc-Air batteries would be good. Well, again, not that easy. The reactions that should happen in Zinc-Air batteries do happen, but very slowly. To increase that reaction rate, scientists like myself will add catalyst to the battery, then increase the energy efficiency of Zinc-Air batteries so they're more practical for real-world application. This is the focus of my research, developing catalysts that work for Zinc-Air batteries. When it comes to catalysts for Zinc-Air batteries, precious metals, such as platinum and ruthenium, set the bar. These rare earth metals can catalyze the reactions in Zinc-Air batteries quite well, but they reduce the accessibility of Zinc-Air technology because of their scarcity and high cost. Engineering more abundant and low-cost materials into catalysts for Zinc-Air batteries is truly the goal of my research. One of the contenders for non-precious metal catalysts are transition metal oxides, like manganese oxide or iron oxide. To engineer these materials as catalysts, we often synthesize nanostructures of the metal oxides, which have increased catalytic activity because of the abundance of surface area. In my research, I use atomic layer deposition, or ALD for short, to make nano-sized layers of these catalysts. I essentially grow the catalyst on the high surface area air electrode in a Zinc-Air battery. ALD works by using a metal-containing gas to deposit metal atoms onto the surface, which is then exposed to an oxygen to create an atomic layer of metal oxide. This process is then repeated over and over again to create a thin film of metal oxide. The gases are able to move around and cover every surface of a high surface area electrode to maximize the total surface area of the final catalyst. And this will help get the most out of a low-cost catalyst. In my work, I've been able to show through electron microscopy and X-ray microanalysis that I can in fact create a 10 nanometer thick iron oxide catalyst on the particles of carbon that make up the electrode. The electrochemical results of the iron oxide catalyst show a lot of promise towards the charging reaction of a Zinc-Air battery. However, 10 nanometers is very thin, and thicker catalyst layers could improve the performance even more. Currently, I'm working on combining 2 or more transition metal oxides, say manganese and iron oxide. This could open the possibility of thicker films and the ability to catalyze both the charge and discharge reactions in a Zinc-Air battery. With lower cost catalysts for Zinc-Air batteries, the amazing benefits of Zinc-Air batteries can be applied to every area of science that's currently struggling with energy storage. Instead of loading up an electric car with many lithium-ion batteries, you could use a smaller amount of Zinc-Air batteries. And when it comes to grid-scale energy storage, Zinc-Air batteries can provide a high energy density, low-cost solution to encourage the use of renewable energy. Ultimately, energy storage can unlock the future of sustainable energy. Thank you for listening.